looking at video 2.1, which is going to investigate atomic theory. How did we ever discover that matter was made up of particles too small to see? Over time, technology improved and our theories evolved, giving us a much more accurate model of the atom. We're going to look more carefully at this in this video. To start off with, we have Democritus in the 4th century BC. He is a Greek philosopher, and he is the one that coins the term atoms. He hypothesized that atoms existed. Of course, technology was not available to test his hypothesis. He stated also that atoms were indivisible. Now, this did create a little bit of controversy at the time. There was also a famous philosopher, Aristotle, that disagreed with Democritus, and there was a specific reason for this. Aristotle did not believe that there could be empty space between the atoms. He supported the existence of what were called the 4 elements at that time, where we have these 4 kind of natural elements. We have fire, and opposite of that would be water. We also would have air and earth, which would be opposite of each other as well. And there's an interface in between each of the pairs. So we have dry, hot, cool, wet, for example. So it makes sense if you study the diamond a little bit. This simple idea went unchallenged for about 2,000 years until we had enough technology to basically prove otherwise, that this idea of atoms was valid. John Dalton was a British school teacher who came up with these 6 ideas based on experiments. And these ideas are really important. It gives us a really strong foundation for what we currently understand about matter, even though it's not totally perfect. But we'll start off with the beginning here, that matter is composed of extremely small particles called atoms. That those atoms are indivisible and indestructible. Atoms of a given element are identical with their size, mass, and their properties. If we have a sample of atoms of a specific element, that element is different from the atoms of another element. The 5th one here is that different atoms can combine in whole number ratios to form compounds. And then lastly, number 6, that in a chemical reaction, atoms are separated, combined, and rearranged. This image shows us how Dalton was looking at a mass ratio during chemical reactions. Here we have a reaction between oxygen and hydrogen, and it forms water, which is something that you are familiar with. He was looking at the mass ratios between these things. If we have 16 mass units of oxygen, it would combine with 2 mass units of hydrogen to create 18. So we're showing the law of conservation of mass here. Now, Dalton did notice a pattern during these experiments that there would be specific whole number ratios with these compounds, and it leads to the law of definite proportions, saying that a given compound will contain the same exact whole number ratios of elements, regardless of the size of the sample that was used. Now, which of these ideas from Dalton's atomic theory are still believed to be true? An atom is the smallest particle of an element that still retains the properties of that element. We can't divide it up anymore and still retain those properties. Here's a comparison of how big atoms are. First, we're going to compare an atom and an orange. So an atom is to an orange as an orange would be to the planet Earth. Big difference in size there. Here's another way to look at it. The diameter of an atom is to 1 millimeter as the thickness of one piece of paper is to the entire Empire State Building height. Big difference. Piece of paper to the Empire State Building. So it gives you a frame of reference as to how big atoms are. Looking at subatomic particles now. We know that Dalton stated that atoms were indivisible, and we know that that's actually not correct. There are subatomic particles, and we do have evidence of that. Those subatomic particles are electrons, protons, and neutrons, and different scientists are credited with discovering each of these particles. We'll start with Goldstein, a German physicist discovering the proton. He discovered that atoms had a positive charge, and he was looking at neutral particles that would give negative cathode rays in an electric field, that they must also then have a positive piece, which is where he developed this idea behind a proton. Thomson is a big name for us. Thomson is English and discovers the electron, and he was a physicist working at Cambridge. He was quite klutzy. He would break his equipment, and a lot of different physicists were using cathode ray tubes at this time. So Thomson discovers the electrons using this device. Here's a diagram of the cathode ray tube. What I want you to notice is that this would be a device made of glass. On the left-hand side is where we would be introducing a beam of electrons. The black area is the cathode ray, which is it would glow, kind of a bluish color. And what I want you to pay attention to also is that there are some charged plates. There's a positive plate at the bottom, and notice that the beam is deflected down towards that positive plate. Keep in mind that opposite charges attract, so it's likely that it's a negatively charged beam. Thomson noticed that if it was a magnetic field, or that he would see this deflection in the same manner, no matter what gas was within this tube, that we would see the negative plate deflect and it would be attracted towards the oppositely charged plate. So the cathode rays were deflected by the negatively charged plate, and no matter what metal was used inside of the tube, same results. This is the model of the atom that he is credited with, called the plum pudding model of the atom. Think of the red pudding kind of like the positive area of the atom. The negative electrons would be like these blue plums included in this diagram. So overall it would be neutral because the red pudding would be canceled out by the negative plums shown there in blue. So again, the plum pudding model, kind of like chocolate chip cookie dough. There was a quote that was kind of capturing how Thomson was so surprised at how small and light the electrons were. It was an insignificant fraction of the mass of an atom. He does win the Nobel Prize in Physics and estimates that an electron is about 1,000th the mass of either a proton or neutron. We now know that the electrons are part of an electron cloud, but that was not part of Thomson's discovery. Robert Millikan is an American scientist who improves the estimates of the mass of the electron using this oil drop experiment. Particles are introduced to the device, and we use the charged plates to kind of suspend those particles in its base and the relationship between their mass and their charge. He estimates that an electron is 1,837th the mass of hydrogen. Now Rutherford in 1906 does this experiment called the gold foil experiment, where we fire alpha particles, which are really like helium particles, at a very thin piece of gold foil, kind of like aluminum foil. Some of those alpha particles, which are heavy, go straight through, which is what was expected, but some of those particles do not. They're deflected at all kinds of different angles. Thomson does win a Nobel Prize for this as well. So here's a diagram. We see the gold foil in the center. We see our alpha source in purple up towards the top. So it's like a gun of, fires alpha particles, which are somewhat heavy, at this very thin piece of foil. We expect them all to end up in the back, in the center, but they're deflected, as you can see, at all kinds of different angles, which was really a surprise. So to back up and think, well, what would cause them to be deflected at all kinds of different angles? So look at this close-up of one atom, and we're firing gold particles from the left-hand side. Firing alpha particles at the gold from the left-hand side, and many of the alpha particles, pass straight through. You can see some at the top and some towards the bottom of the atom, but the ones that come closer in contact with the nucleus are deflected at those various angles, and they conclude that there must be a very, very dense core of positive charge within that nucleus. Rutherford says if an atom was the size of a football field, the nucleus is the size of a marble. Bill Bryson, in his book A Brief History of Nearly Everything, does have some quotes about Rutherford. One saying that all science is either physics or stamp collecting. Rutherford was not really impressed that he won the Nobel Prize in chemistry rather than physics. And he also was known, Rutherford, for being an extremely hard worker. He did not give up. He considered alternative views and other kinds of interpretation of data, which really led him to some unique perspectives. He was prepared, the quote at the bottom, he was prepared to work at it harder and longer than most people and be more receptive to unorthodox explanations. Never give up. Chadwick, and this fascinates me, Chadwick, also English, wins a Nobel Prize, discovers the neutron using a particle accelerator, which is still used for research now. There's bigger and better ones now. He was a student of Rutherford, and I find that that legacy is so unique and important. Niels Bohr was also a student of Ernest Rutherford, and he develops the planetary model of the atom. So think about the nucleus in the center, kind of like the sun is in the center of the solar system. And then we have in the solar system those planets orbit around the or around the sun, kind of like in our planetary model of the atom, the electrons would orbit the nucleus. As an electron moves from one orbit to another, it's like gaining or losing energy, and they're called quantum leaps, and he also wins a Nobel Prize. Here are 3 laws I'd like to summarize. The law of definite proportions is first. This is looking at a given compound containing exactly the same ratio of elements by mass. Next is the law of multiple proportions. This is if we have, let's say, 2 compounds like carbon monoxide, which is a 1-to-1 ratio between carbon and oxygen, and carbon dioxide, which is a 1-to-2 ratio between those two. So we can have different whole number ratios of those elements. Lastly would be the law of conservation of mass, and this says that matter is never created nor destroyed. Thanks for watching.